Algebra 2, you're hearing me tonight with a little bit of a cold. Sorry for the painful noise you're going to be hearing, but we'll get through lesson 15. We're going to be talking about structure in graphs and polynomial functions. I just saw my typo. Sorry about that. So what that means is we are going to graph and describe what's called end behavior. Okay, first of all, the opening exercise, excuse me, sketch a graph of f of x equals x squared. What will the graph of g of x equals x to the fourth look like? Sketch it on the same coordinate plane. And then what will the graph of h of x equals x to the sixth look like? What I'd like to do is compare these a little bit. I did graph f of x equals x squared on the graphing calculator. What I want to do is show you what g of x actually is. Okay, it's x squared times x squared, and you all say, yeah, it is. Good job. And that's why g of x looks very similar. You'll see here, it's a little flatter at the bottom. And then we have h of x equals x squared, x squared, x squared, which is why that graph looks very similar to, just even more flat on the bottom. So the x-intercept for both of these is at 0. So they pass through ordered pair 0, 0. The basic shapes are the same, but near the origin, the graph of g is much flatter than the graph of f. And then the graph of h is even flatter than the graph of g. All of the graphs pass through the origin. Since we're squaring and multiplying by squares, the graph of h should look about the same as the graphs of f and g, but increase even faster and maybe flatter near the origin. So it will decrease faster, flat at the origin, and increase faster. Decrease, flat at the origin, and then increase. And this one's going to decrease slowest and increase slowest. And we'll get to what those words decrease and increase mean as we go through the lesson. Here's where I graphed all three graphs on the same coordinate plane using my graphing calculator. Let me label them for you. This one out here is x squared, and then the next one in is x to the fourth, and the last one is x to the sixth. You'll see x to the sixth has a much steeper slope before it flattens out and goes up, and x squared has the most the gradual slope. All right, a little bit of a discussion. So let's talk about what's called end behavior. End behavior of a graph. It's a way to talk about the function and what happens to its graph beyond the bounded region of the coordinate plane that is drawn on paper or the window in your graphing calculator. When you're in your window in your graphing calculator, you can set the x and the y-axis, but for instance, you're not going to see what's happening past the top of your window no matter what. So we can talk about end behavior. It's a way to talk about what's happening outside of the window because we can't see the entire graph. So let's say let f be a function whose domain, which you remember is input, which is usually the x, and range, which is output, the y, are subsets of the real numbers. The end behavior of a function f is a description of what happens to the values of the function. So we say as x approaches positive infinity and as x approaches negative infinity. And how we would write that is as x approaches infinity, which would be positive infinity, and x approaches negative infinity. We can put a positive here, but just leaving the negative off makes total sense. Okay, right, let's look at this graph right here. Here we have some end behavior. So I'd said we can talk about as x approaches infinity. So here's the x-axis. As x approaches infinity, which that's what our axis is doing, it's going towards infinity. So as x approaches positive infinity, what is our graph doing? What is our f of x doing? It is also approaching infinity. So as the values of x increase, our graph is also increasing. As x approaches negative infinity, what is our graph doing? Our graph is also approaching negative infinity. So as our values of x get smaller and smaller and smaller and closer to infinity, our f of x or our y values are also going towards negative infinity. And this is really what we're doing. Okay, moving on. You see here, this is a basic graph of an even degree. Even degree means x squared, x to the fourth, x to the sixth, etc. Okay, these are our degrees, and they have to be even numbers. Now, when it's a positive, our even degree looks like this, and this is our end behavior. Now, when our graph is negative, even degree, our graph is upside down, and this is our end behavior. You could type into your graphing calculator, for example, 1 minus x squared, which would be your negative leading coefficient. I know it's not actually leading, but you would always write things with your variable first, and that would be your negative leading coefficient. Or you could put into your calculator something like this, and you would see that the graph opens down, and it would follow the negative leading coefficient and this end behavior. Okay, example 1. Sketch the graph of f of x equals x cubed. What will the graph of g of x equals x to the fifth look like? What will the graph of h of x equals x to the seventh look like? Sketch this on the same coordinate plane. Okay, what you see, we'll do our first one in black. These are going to be very basic sketches. You'll see the graphing calculator one in a little bit. So this first one is going to be, remember, more gradual, not very steep. Our second one, x to the fifth, a little steeper. And our last one, x to the seventh, yes, even steeper. Okay. Compare and describe the behavior of the value f of x as the absolute value of x increases without bound. So our end behavior would say, as x approaches infinity, f of x also approaches infinity. And as x approaches negative infinity, f of x approaches negative infinity. And here I graphed them all in the same. So this first one was x to the third power, then we had x to the fifth power, and then x to the seventh power. And you see here, odd degree, that's our function, and that's our end behavior. So odd degree is third, fifth, seventh, etc. And down here we have negative leading coefficient and what our end behavior is. I'm going to pause right now and just remind you, this graph isn't particularly in your classwork, but it really sums up this part of the lesson quite well. So I would take the time to write it down. Okay, what about f of x equals 4 minus x? I would say that it's negative leading coefficient, but is it even or odd? Well, to the first power is odd, so it's a linear function. Does it follow the end behavior? I didn't graph that well. This would have a... It does. As x goes to infinity, f of x also goes to infinity. As x goes to negative infinity, f of x also goes to negative infinity. Okay, exercise 1. Consider the following function. With a mixture of odd and even degree terms, predict whether its end behavior will be like the functions in the opening exercise or more like the functions from example 1. Graph the function f using a graphing utility to check your prediction. Okay, let's talk about it. We see here our leading coefficient is positive and an even degree. So my guess is going to be it's going to act like an even positive function. I have it graphed on the next page. Hold on. So we see here that it acts more like an even degree monomial. Function. Cool. So you see here, this is what it looks like. So as x is going towards infinity, my f of x is also going towards infinity. As x is going towards negative infinity, my f of x is going towards positive infinity. Really quick, this is what I did. Okay, in my y equals, I put the whole function in. You can't see the rest of it in the window. This was the window that I set up so that I could see it like this. Okay, next, consider the following function. Look at our leading coefficient is positive and odd degree. Predict whether its end behavior will be like the functions in the opening exercise or more like the functions from example 1. Graph the function f using a graphing utility to check your prediction. So I've graphed it on the next page. I think it will look like an odd degree positive. So this acts like a positive odd degree monomial function. So our conclusion that we're drawing here is polynomials act like their highest degree monomial. Yep, you see here, as x is going towards infinity, our function is also going towards infinity. As x is going towards negative infinity, our function is also going towards negative infinity. I didn't give you the details of the window and such because it didn't change. Okay, you already saw this page. Thinking back to our discussion of x-intercepts of graphs of polynomial functions from the previous lesson, sketch a graph of an even degree polynomial function that has no x-intercepts. No x-intercepts, even degree. I'm going to sketch it first and then we can try to come up with the graph. This right here is an even degree. So to me, it looks like an x squared. And the y-intercept is at 2. So that's exactly what I drew. It doesn't have an x-intercept. Similarly, you can sketch a graph of an odd degree polynomial function with no x-intercepts. An odd degree, looks like this, or looks like this. I can't actually sketch any of those on this coordinate plane because I'm always going to cut through somewhere. It's near impossible. Nope. Can't do it. So basically we can conclude that graphs of graphs of odd powered polynomial functions always have an x-intercept, which means that odd degree polynomial functions always have at least one zero. Odd, that's not readable, there we go. Odd degree polynomial functions always have at least one zero. And that polynomial functions of odd degrees always have opposite end behavior. Always have opposite end behavior. That opposite end behavior just means as x goes to infinity and x goes to negative infinity, your f of x will be opposite. For instance, if it's positive, it looks like that. No, that's not. There we go. If it's negative, it looks like this. And it's just opposite of each other. All right, let's try this one. The Center for Transportation Analysis studies all aspects of transportation in the United States, from energy and environmental concerns to safety and security challenges. A 1997 study compiled the following data of the fuel economy in miles per gallon of a car or light truck at various speeds measured in miles per hour. The data are compiled in the tables below. Plot the data using a graphing utility. Which variable is the independent variable? Okay, I need you guys to get out your graphing calculators. Okay, we're going to try to go through how to use them. So we just plotted the data using a graphing utility. Which variable is the independent variable? I put that into list 1. It is independent. Okay, let's see what other questions it's asking. It seems that I didn't put part B down here. This data can be modeled by a polynomial function. Determine if the function that models the data can have an even or odd degree. We've already said even because of how it looks. And actually, I'm going to show you on this slide. All right, so first thing I did was I took this table, and in my graphing calculator, I pushed the stat button. Okay? After I pushed the stat button, I pushed the edit button, and you see here I have list 1 and list 2, and I populated the list. It took a little bit of time, But I took all this data right here and I put one into list 1 and the other one into list 2. Okay, and once you finish that, you can go to second stat plot and turn on one of the stat plots. So statistics, that's what we're using. So we're going to turn on the first stat plot, which you see here for mine has list 1 and list 2 is what it's going to graph. And since I just populated list 1 and list 2, I'm good. So you're going to select this right here, turn it on, and pick what kind of graph you're going to look at. Once you go into it, you'll see, like I picked this one. You can pick different ones. It depends on whatever you want to use, how you want your graph to look. And you can play with it a little bit, and I'll help you tomorrow. The next thing you want to look at is the window. So if you hit this button right here, you can change your window. And that's just when you graph it, what your opening is, what your x-axis and what your y-axis is. All of these numbers are positive, so your graph is going to be in this quadrant somewhere. So I did an x-min of 0 and x-max of 75, because that's right there. You could have done an x-min of 15, but I just had a little buffer there. My scale was 1, so I'm going by ones. Then a y-min of 24 and a y-max of 34. Okay, 24.4 is my smallest, and 32.4 is my largest. So I hit the button graph, and this right here is what was plotted. Pretty cool. Okay, I'm going to go back a few slides. Hold on. We can actually use the statistics buttons on our calculator to come up with an equation, and I'm going to show you how to do that really quick. So the first thing I did, excuse me, here is I graphed it, and then I went back to the stat part of the calculator and I highlighted calculate. Okay, we said it was even. If you look at our options here, we have a linear regression, which would be ax plus b, but linear is to the first power, which is odd. Quadratic regression, which is x squared. Cubic regression, and quartic regression. I think there are more, but so I selected quadratic regression, which you see right here. I'm sorry, you see right here, 1, 2, then 3. My X list was list 1 because that was my independent. My dependent was list 2, and I calculated it. And this right here, I actually got an equation. So using this equation right here, I've got my A term, which is negative, my B term, my C term, and this number right here sort of gives you an idea if the data is valid or not. That r squared value, the closer it is to 1, the better your data is. So I could, in essence, write an equation for this data. Given this parent function, plug in A, B, and C, and I would have a nice equation for the data. Is the leading coefficient of the polynomial that can be used to model this data positive or negative? Let's think about what we learned. Okay, our graph, if it's an even degree, would look like this. If it were positive, would look like this if it were negative. So what do you think? Is it positive or negative? I agree. I think it's negative because it opens up like that. It's not quite right though. Let's erase this and just give you quadrant 1. It looks something like that. So we put the x variable was speed, and that's independent. The y variable was fuel economy, and that was dependent. We believe the leading coefficient is negative, since the end behavior of this function is to approach negative infinity on both sides. Let's see. It hasn't asked me what degree it is yet. What do you guys think? Do you think it's an even degree or an odd degree? I would say even. We'll get to that in a second. List 2 possible reasons that the data may have the shape that it does. We could say that fuel economy improves up to a certain point, up to a certain speed, but then wind resistance at higher speeds reduces fuel economy therefore increased gas is needed to go higher speeds. Pretty cool. I'm going to go back a slide. Done here. All right, we're done. Relevant vocabulary. Even function. Let f be a function whose domain and range is a subset of real numbers. So an even function, the function f is called even if the equation is true for every number x in the domain. Okay, we're squaring it or cubing it, etc. Not cubing. To the fourth, etc. So if we plugged in a negative, it would become a positive. Even degree polynomial functions are sometimes even functions and sometimes not. Okay, we look at the highest degree to say if it's even or odd. Odd function, if we plug in a negative, we would get a negative answer. Odd degree polynomial can be just a monomial or just look at the highest degree. Good job today.